I will be talking today about development of critical embedded software. So I will do a little introduction on what it is, what are the main criteria to consider, and will present a model-based approach from Ansys on how to improve the outcome of development and the quality. So here we go. So yeah, I introduce myself. I'm Jair Gonzalez. Gonzalez. I have more than 25 years of experience when it comes to embedded software, embedded systems in general. I did engineering, then a master's and a PhD, everything related to different kinds of embedded systems and software. I also worked in Hewlett Packard. I worked in a laboratory called Simberstaff, and in a university in Mexico called the ITESM. I've been working in Ansys since 2013. So today I am Senior Principal Applications Engineer. I am in charge of a global strategy to extend the footprint of Ansys embedded system tools in all industries. All right. So here you have my contact info. Don't hesitate to come back to me whenever you have a question or any comment that you would like to pose. Okay. So Ansys. Ansys has a very big number of tools and then is well known when it comes for physical based simulation. But this time I will speak about embedded software. All right. In the idea of Ansys, we should have the possibility to simulate a whole system, a whole airplane, a whole car, and an important component of every system today is the embedded software. All right. So what is an embedded software? It's a component of what we call an embedded system. So what it is an embedded system? So in fact, it is a system that is composed with a computer, a specialized computer, which is this system is designed to perform a specific task. Like, for example, in the drawings, you see a coffee machine. So the task of this embedded system is to do coffee, right? And then it has different modes of operation. So you remember you have several buttons, and then you can choose the size of the coffee. You can choose if you want to have milk or if you can change the temperature and so on. So all this control is done thanks to a computer that is inside. All right, so we have more examples, not only coffee machines, but also washing machines, refrigerators, ovens, all these kind of appliances that need some or have several modes of operation or complex task to achieve. Then this is done with an embedded computer inside. But we have other kind of more sophisticated embedded systems, like, for example, cars, like, for example, aircraft, like, for example, satellites and robots and your smartphone. All these, they are computers, specialized computers that satisfy a specific task, specialized task for you. All right. And basically, we can say that an embedded system is composed of embedded software and embedded hardware. All right. So the embedded software is used to control, to describe the behavior of the system in general. And usually we use C or assembly language, yeah, to describe. But we'll see that it might not be the best idea. Why it might not be the best idea? Because when you are developing this kind of systems, embedded systems, there are many things that you have to consider. First thing, of course, is functionality. All right. Imagine you want to develop an embedded system that controls flying of an aircraft. It's very nice because you just describe the coordinates and you ask the airplane to go to those coordinates and it will do. All right. So the functionality is very complex, you could imagine. But it's not the only difficulty when you are developing, right? Because as soon as you start with complex functionality, then you very soon start having mathematical challenges, numerical methods, digital signal processing, and this kind of knowledge needs is necessary for the programmer to have. Okay, and but it's not only this. He will have to implement this functionality and these methods and this signal processing analysis with a language. I said before it could be C or it could be ADA or any other language, and this is complex because we are not only caring about describing the functionality, we are caring also about performance. The embedded system has to achieve a task in a given amount of time. You cannot wait forever for the coffee to be ready, or you cannot wait forever for an equation to be solved and give direction to the airplane. All right. So performance is very important. So you need to think about the platform that will be used to execute this program. So you see, the engineer has to consider many different aspects, and we have not finished because if we are talking about a coffee machine, is not a problem. But if we are talking about an airplane, we have safety standards to satisfy. You have to demonstrate that you use the best methods in order for you to be allowed to fly. All right. If you don't demonstrate this, the airplane cannot fly. And safety standards, they imply verification and validation. Very extensive and enormous amount of tasks and effort to be done to verify, to validate that your implementation is well done and is correct. Okay, so if you are using a safety standard, you will end up doing 3 or 4 times more effort if compared to no a regular system, right? Something that is not critical. So as you want to do verification and you need to validate, one of the steps is to verify that you wrote the code. If you did it with C code, for example, or ADA, it has to be readable. It has to be possible for somebody else to come and look at it and read it and understand what is it going on, and to understand if it's well done. So in order to be readable, then you have to follow a standard, a way of coding a number of indentation spaces you have to use, the naming of variables, inputs, outputs, etc. Is a lot of rules that you have to follow and that you have to consider. So this engineer is not, so is most complex activity, which is caring about the functionality. Is not just that. It's a verification, validation, standards, and then it is always in a collaborative project with different versions. Uh, and if it was not enough, it has to be on time because there is competition always. There are milestones that have to be met and deadlines that have to be accomplished. All right. It's too much for every single line of code to be considered, all these different aspects. The software engineer will not manage. Definitively, we need better methods and we need better tools to describe the behavior of the computer. All right. So usually what we do is we use traditional point tools for individual tasks. So the design engineer, he can use uh, text editor for coding, and then the verification will use Word to describe the test cases, and then the safety engineer, he will use an Excel page. There is a lot of different tools, there is a lot of different documents, and they are not directly related. It's very difficult to keep consistency in this way of working. All right. If we ignore what are the best methods and if we ignore what are the best tools, we risk to have this kind of situations. All right, we risk to not achieve high quality or safety in the most important components of our systems. Like for example, for a car, an electronic throttle control system regulates the speed of a car. All right. So is this classical cruise control software or cruise control system that you select the speed at which you want the car to go, like, I don't know, let's say 50 miles per hour, but you want the regulation to stop automatically if you press the brake. But what happens if the software is not well done and it will not stop even if you brake? It will not even stop if you try to turn off the car. So it happened in this case. A car from this car maker simply was not responding to the brake and continue accelerating is what we call as unintended acceleration, and there was the accident. All right, so they had to face court, and they had to pay back a lot of money in order to cover all the damages that happened. All right, after an analysis from NASA, they found out that the software was not following the best methods and clearly were not using the best tools. All right, so number of uh, fishy situations like risk of overflow, nested interrupts, a lot of mirror violations, untestable functions, and so on, which made difficult to verify, make sure that the software was safe or not. All right. So this is what can happen if we don't use the best methods and tools. So the methods, they exist. I mentioned before, the standards are existing for different industries. And in these industries, the embedded systems and the embedded software, of course, has to be developed in a way according to the guidelines from these standards. All right. So, like for example, for aerospace, we have DO 178. For automotive, we have ISO 26262. For railways, we have EN 50128. And like this, there are many standards, even for appliances, for industrial, for nuclear plants, etc. They have a guideline on how you have to develop the software and in the system in general in such a way that we minimize the possibility of an error. All right, in such a way that we reduce the risk to something that is acceptable. Right. And we have authorities that are looking at developers, to make sure that you follow the standards, that you follow the guidelines. And as I said before, if you don't demonstrate that this is the case, then you are not allowed to proceed. All right, simply like this. So these are methods, but I mentioned before, using these methods imply a lot of effort, a lot of verification. Right, so we need more methods. And there exists this method that is existing for forever, I could say, for many years. Architects, civil engineers, they model in order to have a clear understanding on what is going to be constructed. All right, so this is very natural. We know that we have the plans, and we can describe the distances, the volumes, the positions of the different elements of the construction, and so on. It's very simple. And then later we can enrich the model and to make it 3D and to make a very interactive and so on. That's very possible. We never consider doing houses like using a list of instructions on what you want to do that you have to read, the constructor has to read and follow in order to build up the house. It doesn't happen. Why? Because it will imply many lines, and it will imply many documents. One document for the construction, one document for the electricity, one document for the hydraulics. Very difficult to use, right? So text is verbose and is not precise, and it leads to complexity, ambiguity, and inconsistency. Of course, model-based design gives you easier way to design, to modify, to maintain, evolve, etc. This is very clear. We know, all right? And Ansys offers the same for software. Okay, in software with Ansys, you have also the possibility to model, to have a schematic and describe the behavior of the system. So in this case, this is a risk control state machine that describes the behavior of this uh, uh, automatic regulation from a car. And yeah, of course, you need to learn to like for an architect, you need to know how to read the plans. In this case, you need to know how to read the schematic. but very quickly you find out what is the behavior of the computer, what is the behavior of the software. So this is model based. You describe in models in an abstract way what is going to be the behavior of the computer. And with Ansys SCADE, you generate this code automatically. So here we have all this long list I mentioned before, a long list of instructions that the computer follows in order to describe the behavior of the system. All right. So you imagine it's much easier to verify a schematic compared to verify the code, the lines of code. All right. So as in standards, they require verification. Well, this is already one positive point for model based, but it's not the only one. So again, we demonstrate that models, as for architecture, in the case of software, is easier to design, to develop, modify, maintain, evolve the behavior of the computer. All right. So in the case of ANSYS, we provide a tool chain. There is and it's not uh, is a tool chain that you use to develop complex systems, starting from system description with a SysML modeler, system modeling. You describe the architecture of the system, the functions of the system. Then we use Medini Analyze to describe the analysis of whether the system is safe or not, whether the system needs redundancy, duplicity, etc. And then once we found out that, we enrich the system model and we detail further in different components. So one of the components of the system will be the software, can be graphical or it can be control. And then we also describe further the mechanical and physical aspects with other tools from ANSYS. Later, we can actually simulate the whole using Twin Builder, considering not only the physical simulation, but also the control aspects and the graphical aspects, the HMI aspects, all right, until we are able to deploy. So all this is offered in order to facilitate the design and to increase the speed at which you will produce your software, basically focusing only on the most important aspects of the activity, which is design, and then letting verification to be solved in an automatic way. So what are the benefits of using model-based design? Is first, with the SCADE language, you achieve correct by construction. From the beginning, from the moment in which you are modeling the behavior of the computer, the environment is correcting you in the case you forgot initializing a variable or you are mixing variable types, etc. All this is identified at design time and is requested to correct. All right. Once you have a good design, automatically you will generate the code. All right. And you will also generate automatically the documents. All this reduces the errors because there will not be errors in the code, there will not be errors in the document, and then you will speed up the process of development of the embedded system and embedded software. Also, you will reduce or eliminate the effort to plan, to design, to code, and to test the software. If we compare, uh, we could have comparing the manual development of a high critical software against using SCADE method. So when you see at the graphic, we have a huge reduction in the effort to develop the plans, a mild reduction in the part of designing, because remember, you are requested to correct errors from the beginning. So from the moment in which you are designing, you are already correcting errors. Of course, you reduce enormously the amount of effort to code and also to test, because now you don't have to test the code. You test the model and that's enough. So that means you focus on functional testing, but you don't do unitary testing. All right, you don't have to worry about the implementation from design into the code, because that was solved for you. you trust the code that was generated by the code generator. All right. And then you also reduce the effort to integrate software with software or software with hardware, and also more than half the documentation that is necessary to certify. And the whole accumulated, you reduce by half the all required effort to develop a safety critical system, a safety critical software. All right. But there is a condition to have this benefit from model based design. All right. The condition is it has to be qualified or certified. All right. You have to trust the code that was generated from the code generator, because otherwise, if it is not trustable, if it was not certified, if the authorities didn't come and stamped as a certified code generator, then you have to do again the effort of verifying. All right. Okay, you didn't code, but you will still have to test, which you see is a huge differentiator. You still will have to test the integration, and you will still have to generate documentations and so on. And you will still have to do plans because you cannot rely on what is already done for you. So if you really want to get benefit from this model, the tool has to be certified and qualified. By whom? By the same authorities we mentioned before. These authorities, Federal Aviation Administration, EASA, TÜV, etc., according to the kind of activity that we are eliminating or alleviating with the tool. All right. In the case of SCADE, for model-based software design, these code generators they have been already certified for aerospace, for automotive, for railways, etc. All right, up to the highest levels of safety, like DEL A for automotive, sorry, for aerospace, ASIL D for automotive, and so on. So there are different tools, modeling tools with different objectives. All right. So we have, as example, MATLAB Simulink is a very good tool. Everybody knows. I think is present in many companies that are doing, uh, uh, yeah, development of sophisticated embedded systems, and is basically used to prototype or to design the control law. All right. They are based in what we call solvers. So means the behavior that we obtain from the model we cannot know. It's an approximation. It's an implementation of a solver. It doesn't represent one to one the behavior of the software. All right, but very quickly you can figure it out what is going to be the functionality. All right. In the other hand, we have a SCADE. Is DNA, is computer science meant for develop safety critical controllers. When SCADE was conceived for safety critical software, is compliant to the stringent safety standards. So the best methods I mentioned before. And yeah, contrary to Simulink, is not applicable to finance, biology, etc., as MATLAB is perfect tool for that. So in the case of developing a safety critical system, we could use the best of each one. So Simulink to prototype the control laws, to design the control laws, and SCADE to develop the safe software. All right, so let's consider again this cruise control system. We have yeah, the user command, then we have the behavior of the system and a feedback for the system. So first, what we do normally is a system response study, and then control law prototyping, for which MATLAB Simulink is a perfect tool. It's a very good tool with a lot of toolboxes helping you to develop these control laws. And once you have the parameters, you have the coefficients, etc., you can use those coefficients in a software model implementation with the SCADE, and to finally have a certified code generation from here. All right. So This is a very good tool chain where you taking the best out of different modeling tools to achieve your embedded system. Remember that with Ansys SCADE, code is equal to model, so no need for save subset, no need for code reviews, no need to back-to-back testing, no need to do code coverage, because the code generator has been certified to the highest levels of criticality, and has been demonstrated that the code generated is one-to-one equivalent to the model behavior. All right. So we have many references in aerospace and automotive using our tools thanks to these benefits. All right. So yeah. So going to the end of the talk, just if you would like to get to know more, please come to the web page. You have ansys.com, where you can look at the products, careers, students and academic, contact us and so on. We have a lot of facilities to give you access, to help your company, to help you in your project, in order to take the best out of model-based design tools, either for physical simulation or for software design.